In this video, we will discuss logarithmic expressions, equations, and formulas. A logarithmic expression is an expression that contains at least one term with a logarithm. The three basic components of a power are the base, exponent, and result of exponentiation or power. In the exponential expression, 3 to the fourth equals 81. 3 is the base, 4 is the exponent, and 81 is the result of exponentiation. Another form of this equation is the logarithm. The logarithmic form is log base 3 of 81 equals 4. This is an equivalent form that simply moves around the numbers that we've been given, but allows us to find the exponent more easily. In other words, these two expressions are equivalent. X equals b to the y, and log base b of x equals y. To write an exponential equation as an equivalent logarithmic equation, if x equals b to the y, then log base b of x equals y, provided that b is greater than 0 and does not equal 1. The exponent in the exponential form is the dependent variable in the logarithmic form. The base in the exponential form is the base in the logarithmic form, and the dependent variable in the exponential form is the result of exponentiation in the logarithmic form. This result is sometimes referred to as the argument. Write the exponential equations in logarithmic form. A, 2 to the fourth equals 16 is equivalent to log base 2 of 16 equals 4. 3 squared equals 9 is equivalent to log base 3 of 9 equals 2. 2 to the negative 2 equals 1/4 is equivalent to log base 2 of 1/4 equals negative 2. To write a logarithmic equation as an equivalent exponential equation, log base b of x equals y converts to x equals b to the y, provided that b is greater than 0 and does not equal 1. The dependent variable in the logarithmic form is the exponent in the exponential form. The base in the logarithmic form is the base in the exponential form, and the result of the exponentiation in the logarithmic form is the dependent variable in the exponential form. Write the logarithmic equations in exponential form. Log base 2 of 32 equals 5 is equivalent to 2 to the fifth equals 32. Log base 3 of 81 equals 4 is equivalent to 3 to the fourth equals 81. Log base 5 of 1/25 equals negative 2 is equivalent to 5 to the negative 2 equals 1/25. Log base 10 of 0.001 equals negative 3 is equivalent to 10 to the negative 3 equals 0.001. When the base of a logarithm is 10, the logarithm is referred to as a common logarithm. If the base is omitted in a logarithmic expression, the base is assumed to be 10. Thus, log base 10 of 1000 equals 3 is normally written log 1000 equals 3. On a calculator, expressions containing common logarithms can be evaluated using the log key. A logarithm with a base of e is a natural logarithm and is abbreviated as ln. Calculators normally have an ln key. Thus, log base e of 1 equals 0 is normally written as ln1 equals 0. Expressions containing natural logarithms can be evaluated using the ln key. For most logarithms, we must use a calculator or computer. Evaluate the logarithmic expressions. Log of 10,000, we can evaluate this without a calculator. 10,000 equals 10 to the fourth, so log 10,000 is 4. Log of 0.000001, we can evaluate this without a calculator. 0.000001 is 10 to the negative 6th, so log of 0.00001 is negative 6. Log 9, we must use a calculator to evaluate this. Log 9 is 0.954242594, which is about 0.9542. Log of 5.4, we must use a calculator to evaluate this. Log 5.4 equals 0.73239375998, which is about 0.7324. Evaluate the logarithmic expressions. These expressions require use of a calculator. The natural log of 5 is 1.6094. The natural log of 4.5 is 1.5041. And the natural log of 948 is 6.8544. Most calculators do not have buttons that will allow us to simply evaluate logarithms with bases other than 10 or e. There are two possible ways to handle such logarithms. If we can rewrite the logarithm in the form x to the a equals x to the b, we can evaluate the logarithm by solving such an equation. For example, if we have the equation log base 4 of 256 equals x, since 256 equals 4 to the fourth, we can rewrite this equation as 4 to the x equals 4 to the fourth, and thus x equals 4. Likewise, if log base 3 equals 1/27th, log base 3 of 1/27th equals x, since 1/27th equals 3 to the negative 3, we can rewrite the equation as 3 to the x equals 3 to the negative 3, and x equals negative 3. If we cannot rewrite the equation this way, we must use the change of base formula. To evaluate a logarithm with base b other than 10 or e, use the property log base b of a equals log a over log b. This is called the change of base formula. A similar property can be used with natural logarithms. Log base b of a is the natural log of b over the natural log of a. To check, evaluate b to the x, where b is the base of the logarithm and x is the logarithm. The result should equal the argument. Evaluate using the change of base formula. You will need a calculator. Log base 7 of 343 is log of 343 over log of 7, which is 3. Log base 4 of 256 is the log of 256 over the log of 4, which is 4. Log base 3 of 81 is log of 81 over log of 3, which is 3. I'm sorry, that should be 4. That should not be 3, it should be 4. The loudness of sound is measured by a unit called a decibel. A very faint sound, called the threshold sound, is assigned an intensity of I0. Other sounds have an intensity of I, which is a specified number times the threshold sound, I equals N times I0. Then the decibel rate is given by the formula dB equals 10 log I over I0. Find the decibel rating to the nearest decibel for sounds having the following intensities. A whisper, 110 I0, has a decibel rate dB equals 10 log 110 I0 over I0, which is 10 log 110, which is 20. About 20, it's not exact. A speaking voice, 230 I0, has a decibel rate dB equals 10 log 230, which is about 24. A jet plane at takeoff, 109 trillion I0, has a decibel rate 10 log 109 trillion, which is 140. To find the time for an investment to reach a specific amount if compounded continuously, t equals the natural log of a minus the natural log of p over r, where t is the time in years of investment. A is the accumulated amount, p is the principal amount, and r is the annual interest rate. Find the length of time for 32,750 to reach 47,650.97 or $47,650.97 when invested at 5% compounded continuously. Here, A equals $47,650.97, P is $32,750, and R is 0.05. So T equals the natural log of A minus the natural log of P divided by R, which is the natural log of 47,650.97 minus the natural log of 32,750 over 0.05. I'm not going to go through those intervening steps. This comes out to about 7.5 years. We graph logarithms using a table of solutions. For example, graph the function f of x equals the natural log of 4x using x equals 0.125, 0.25, 0.5, 1, 2, 3, and 4, and determine the domain and range. Values in the table below are approximate. I'm not going to go through all the values, but those are the points that we get from this. The graph appears on the next slide. Note that many of the points do not precisely line up with the graph because they are approximate, not exact. The domain of a logarithmic function is generally all real numbers greater than 0. The range is all real numbers. The following properties of logarithms are useful in simplifying logarithmic expressions. Equality of logarithms: if log base b of x equals log base b of y, then x equals y. Logarithm of a product: log base b of mn equals log base b of m plus log base b of n. Logarithm of a quotient: log base b of m divided by n is log base b of m minus log base b of n. Logarithm of a power: logarithm of b, log base b of m to the n power equals n times log base b of m. Logarithm of quantity with the same base: that's log base b of b equals 1, and logarithm of 1, log base b of 1 equals 0. Solve the equation log base a of d equals log base a of c minus k times log base a of p for d. So log base a of d equals log base a of c minus k times log base a of p, which means that log base a of c minus log base a of p to the k by the logarithmic power property, which is equal to log base a of c over p to the k by the logarithmic quotient property, which means that d is equal to c over p to the k by equality of logarithms.